Dear students, in this class we discuss the one-way ANOVA procedure. Let me first consider a definition. Suppose that the variable under consideration is normally distributed on each of the k populations. In the examples, energy consumption is the variable. The k populations are households in 4 regions. So we assume that energy consumption in 4 regions are normally distributed. And also assume that the population standard deviations are equal. That is, sigma 1 square is equal to sigma 2 square is equal to sigma k square. Then for independent samples from k populations, the variable f is equal to MSTR, MST treatment mean squares divided by the quantity mean square error follows f with the degrees of freedom of MSTR is k minus 1 and n minus k for MSC. So this quantity follows f with k minus 1 degrees of freedom in the numerator and n minus k degrees of freedom in the denominator if H0 of equal population means are true. If H0, mu1 is equal to mu2 is equal to etc. mu k is equal to 0 is equal to mu k is true. If this is true, then this quantity follows F distribution. And it requires 2 things. One is that the population, the variable under consideration is normal on k populations. The second condition is that population standard deviations are same. And we now have all the elements required to formulate a procedure for performing one-way ANOVA test. But before performing the hypothesis test, we have to consider 2 more concepts. One is one-way ANOVA identity. One-way ANOVA identity. One concept which we discuss in the context of one-way ANOVA is one-way ANOVA identity. First, to explain what is this one-way ANOVA identity, we first consider a third sum of squares, a measure that provides total variation among all the sample data. Total variation among the entire sample data. It is called total sum of squares, SST. Total sum of squares, SST, and it is equal to sigma xi minus x bar square. X bar is the common x bar. Xi is the values of the variable from all the populations. So, total sum of squares, sigma xi minus x bar square. It is called total sum of squares and defined it as sigma xi minus x bar square. Total sum of squares. Now, if we divide SST with n minus 1, we divide this with n minus 1. Suppose n minus 1. We get a sample variation of all observations. Sample variation of all the observations. So, SST is a measure of what is known as total variation. Is a measure of total variation. Now, in the example we have considered, x bar is equal to 11.1 and SST applying the formula becomes 179.8 and we know that SSTR is equal to 97.5, SSE is equal to 82.3 and it follows that 97.5 plus 82.3 is equal to 179.8. That means SST is equal to SSTR plus SSE. That is, total sum of squares is equal to treatment sum of squares plus error sum of squares. And this equation is known as one-way ANOVA identity. SST is equal to SSTR plus SSE is known as one-way ANOVA identity. Remember this always. SST is equal to SSTR plus SSE. SST divided by n minus 1 will give you what is known as the measure of total variation. Measure of total variation. Now, this is one concept which we consider. A second is one-way ANOVA tables. We use one-way ANOVA tables to calculate the F. One-way ANOVA tables to calculate F. And one-way ANOVA table is highly useful for organizing various sum of squares and to calculate the F statistics. Now its format is, let us see what is the format of an ANOVA table. Source of variation, degrees of freedom, sum of squares, MSS is equal to SS by degrees of freedom, F. That is, first is treatment, K minus 1, SSTR, MSTR is equal to SSTR by K minus 1, error n minus k, SSE, MSE is equal to SSE by n minus k and F is MSTR by MSE provided that H0 is true. And if you, and there is one more, total n minus 1 SST. If you add n minus k with k minus 1, you will get it as m minus 1, total degrees of freedom. In the example above, these values are 3, 16, 19, then SSTR 97.5, 82.3, 179.8 quantities we have calculated, 32.5, 5.144 and F is 6.32. Now this is the typical ANOVA table. This ANOVA table helps us to organize and summarize our data, which will make calculation easy. Now we are ready to explain how to perform a one-way ANOVA. To perform a one-way ANOVA, we require three things. One is SSTR, the other one is SSE, the third one is SST. SST, SSTR, SSE formulas are given. But when you calculate the formulas by hand without a software or something, we use the computational formulas. It is just for your understanding only, the computational formulas, SST, defining formula and computing formula. SST, sigma x minus x bar square. For computation, we can use it as sigma x square minus sigma x the whole square by n. This formula is familiar to you. SSTR, sigma nj into x bar j minus x bar square. For computation, we use the formula sigma tj square by nj minus sigma x square by n. SSE for computation, sigma nj minus 1 into s square j, and for computation we simply take it as SST minus SSTR. J is equal to 1 to k, and x bar is the overall mean, nj sample size of the jth population, x bar j is the mean of the jth population, s square j is the variance of the jth population, and tj for calculation is the sum of sample data from population j, sum of sample data from population j. These are the computational formulas, but if you are doing the problem manually, you can use it, otherwise you can simply ignore it. Now let me explain the steps of one-way ANOVA. We have 4 assumptions: simple random samples, independent samples, normal populations, equal population standard deviations. These are the 4 assumptions that we have discussed. Now, what are the steps? Step 1 is formulation of H0 and H1. Mu1 is equal to mu2 is equal to mu k. What is H1? Not all these means are equal. In the second step, we decide alpha, the level of significance. The third step is obtain 3 sum of squares, SST, SSTR and SSE. The fourth step is construct the one-way ANOVA table and obtain F. Then from the table obtain F alpha, the critical F, with the degrees of freedom k minus 1, n minus k. And if F greater than F alpha, reject H0. In the example we have considered, for alpha is equal to 5%, alpha is equal to 5%, F is 3.24, critical F, and the F we have obtained is 6.32. As the empirical F exceeds the critical F for the given degrees of freedom, we reject the null hypothesis and conclude that energy consumption in the regions are all not identical, they are different. And this is what is meant by one-way ANOVA. And remember this, if you want to practice, you go through any book of statistics and work out the problems yourself. If you are using a software, you just input the data and click on the appropriate buttons and you will get the result and interpret the results. Remember SST, SSTR, SSE, etc. The procedure, comparison of variation between means within samples and the ratio, and also one-way ANOVA identity. These are some of the terminologies associated with the one-way ANOVA. One can go beyond one-way ANOVA, two-way ANOVA, ANCOVA models, ANOVA with and without replication. It is a vast area, and these are provided in standard books.